Hi everyone, I'm Susana and I'm going to be talking about the effects of non-standard interactions on the future neutrino solar sector. So just briefly to begin, I wanted to say that this was work done in collaboration with Pablo Martinez Miravé and Mariam Tortora here at IFIC in Valencia. And I'd like to take the opportunity to encourage you all to go and see Pablo's talk on a similar topic and to say that I hope you enjoy the rest of the conference as well. So just quickly, I wanted to give a brief overview of non-standard interactions to explain why we're interested in them, why we study them. So we all know that the standard model as it stands is not enough to explain the nature of particle physics in its entirety. It doesn't provide a mechanism for the origin of neutrino mass. We don't yet have a viable dark matter candidate. And there are plenty of studies about the nature of this potential dark matter candidate and its connection with neutrinos. What a lot of these extensions of the standard model that try to address these unresolved issues in particle physics have in common is the emergence of non-standard interactions between neutrinos and standard model fields. And if these non-standard interactions were strong enough with respect to those of the standard model, then they could be detectable at oscillation experiments or scattering experiments. So this provides the motivation why we study them, why we continue to explore the possibility of their existence and try to constrain what we know so far. Now, in general, NSI can be divided into either charge current NSI, which is mostly relevant at the production and detection moments of neutrino studies, and neutral current NSI, which, though also relevant for the detection processes, affects the propagation of neutrinos through a medium. So this is the one that we're going to focus on for this study, given that it's the most interesting when you're talking about, for example, solar neutrinos, which have to pass through the sun and through the Earth before they're detected and studied. Now, when you include non-standard interactions into the standard oscillation framework, this gives rise to a generalized matter potential, which in turn provokes a modification in the Hamiltonian. So you have here the probability of oscillation between a neutrino of one flavor to a neutrino of a different flavor. And the Hamiltonian here, the Hamiltonian of neutrino oscillation, is given by the sum of the Hamiltonian in vacuum plus the effective potential in matter and the NSI potential. So this is why here you have the modification to the actual process of neutrino oscillation. Now, NSI can also give rise to new sources of CP violation, which is clearly a topic that is subject to renewed attention since the recent tensions between the CP violation measurements of T2K and NOVA. And it can also cause degeneracies in the measurements of the solar mixing angle and the mass ordering. Now, I won't talk too much about this. I'll mention it again briefly later, but this is also associated with what's known as the LMA dark solution to the neutrino problem. Now, further improvements in the constraints of non-standard interactions are expected from the next generation of neutrino experiments because they will be sensitive to subleading effects. For this study, we're going to be focusing on two of them, namely JUNO, which is a future medium baseline reactor experiment, which is expected to be able to measure the solar oscillation parameters with an unprecedented accuracy. And in parallel, Hyper-K, which will be the next generation of the Kamiokande experiments in Japan, and will study the high energy spectrum of neutrinos, of solar neutrinos, with a vastly increased statistical power with respect to its predecessor, Super K. And the complementarity between solar and long or medium baseline reactor experiments has in the past been shown to successfully curtail the existence of non-standard interactions. And so it's to be expected that this will continue in the future. And this forms the basis for our study that I will be talking about today. So our aim is to study the expected sensitivity to both flavor-changing and non-universal NSI with D-type quarks from the combination of these two experiments, as well as to test the robustness of the measurement of oscillation parameters in the face of NSI. And it's important to note here, I want to say quickly, non-standard interactions can be studied within the framework of effective field theories, EFTs, through their parameterization in terms of four fermion operators. And here I just want to state the two sort of effective NSI parameters that we're going to be discussing a lot in this talk. These are dimensionless coefficients that simply quantify the strength of NSI with respect to standard model interactions. And they're associated, epsilon and epsilon prime are associated to flavor changing and non-universal NSI respectively. So I thought that was important to include first. I'm going to move now to the Hyper-Kamiokande experiment, which of course we all know a lot about, so I'll be very brief. But following the success of its predecessors, Kamiokande and Super-Kamiokande, it will be the third generation. It will have a fiducial volume 8.3 times larger than that of Super-K, and that's only considering one tank. There is still a possibility of a second tank being built, either in Japan or further down the T2K beamline in Korea. It will have an upgraded near detector, it will have a new intermediate detector which will be constructed, and it has clearly a huge research potential. So everything from solar and atmospheric neutrinos to supernovae, as I mentioned, the T2K, T2HK beamline, applications to dark matter searches and neutrino tomography, and of course nucleon decay. But what we're going to be focusing on for this talk is its unique capacity to measure and study solar neutrinos. Now, for our analysis, we did a spectral day and night analysis where we included all the uncertainties that the Super-Kamiokande collaboration includes in similar analyses that they have done. So uncertainties in the spectral shape of the fluxes, energy resolution, energy scale, and the normalization of the boron-8 and HEP flux. We accounted for all of these in our simulations. We also did a study on the impact of the exact experimental configuration of the detector. So we looked at variations in fiducial volume and in low energy threshold. We looked first of all at an optimistic scenario where the low energy threshold is comparable to that of Super-K right now, 3.5 MeV. We looked also at a more conservative estimate of 5 MeV, which is in line with Hyper-Kamiokande's current predictions. This would be assuming a lower overall photo coverage compared to Super-K's 40%. And we also looked at the possibility of a second tank being built further down the line, essentially doubling the statistics there. We concluded that all of these variations are of little relevance in this scenario. Further information, and we can discuss it if you're interested. I found that very interesting. But so I just wanted to state that for the next few plots that I will show, and from here on out, we're assuming one tank, 187 kilotons of ultra pure water, and a low energy threshold of 3.5 MeV, so the so-called optimistic scenario. And I'm showing a plot here which shows the effect of NSI parameters, the variation of NSI parameters on the sensitivity of Hyper-Kamiokande to solar oscillation parameters. So you have on the x-axis here the solar mixing angle, on the y-axis the solar mass splitting. And in each panel we're keeping one NSI effective parameter fixed at 0, and the other is being allowed to vary between -1 and 1. And what we see is essentially what you would expect. So given both the different mixing in the production region as well as the modified propagation here on Earth, you would expect NSI to greatly distort the standard picture and to include potentially very large shifts in the values of oscillation parameters. And this is exactly what we see here. So I didn't include the sensitivity of Hyper-K to oscillation parameters in the absence of NSI because I didn't want to overload this talk with plot after plot. So you're going to have to take my word for it. But for instance, on the right-hand side, what we see is that non-zero epsilon prime, so non-zero, non-universal NSI, gives rise to, well, as I say, you'll have to take my word for it, but a shift of an order of magnitude. It affects by an order of magnitude the sensitivity to the solar mass splitting that Hyper-K will have. And as well, I want you to note again on this right-hand panel, this solution arising in the second octant for very, very large values of epsilon prime. That, as I mentioned earlier, corresponds to the LMA dark solution. And we'll touch on that a bit again later. In the left-hand panel, what you see for flavor-changing NSI is a very significant degeneracy between the NSI parameter and the oscillation parameters. And in order to break these degeneracies, it becomes very clear, especially because these degeneracies will substantially increase when you're taking into account both flavor-changing and non-universal NSI. It becomes very clear that to break these degeneracies, additional data sets have to be included. It is absolutely crucial because you cannot resolve these through the study of the high energy range of solar neutrinos alone. And that is where JUNO comes in. So JUNO, as I mentioned earlier, is a future medium baseline reactor. It will, in practice, be a successor of sorts to CAMLAND. So its average baseline is 53 kilometers compared to CAMLAND's 180. Its principal measurement is the same as CAMLAND, reactor neutrinos through inverse beta decay events. So essentially measuring the disappearance probability of anti-electron neutrinos. And compared to CAMLAN, it has significant advantages, so much larger statistics and a much, much better energy resolution. We took all of this into account in our simulations as well. So as I say, excellent energy resolution, excellent sensitivity to oscillation parameters. We included the systematics in the analysis that the JUNO collaboration has themselves. And I just want to note here, so the reactor parameters, θ13 and delta m squared 3.1, current constraints show that they are not substantially affected by matter effects or NSI. So we would expect JUNO to be able to produce a very accurate measurement of these parameters even in the presence of NSI. However, when you look at the solar parameters, so θ12 and delta m squared 2.1, it's a different picture. Matter effects have been shown to play a very large role in the measurement of these parameters. So non-standard interactions, even if smaller in absolute value than the matter effects, could still greatly affect the precision goals of the experiment. And I'm showing now a figure similar to the one I showed for Hyper-K. So again, you have on the x-axis the solar mixing angle, on the y-axis the solar mass splitting. Left and right panel show each of the NSI parameters allowed to vary individually. And what you can see here is you can see that a non-zero epsilon produces a very large shift in the mass splitting. A non-zero epsilon prime affects mostly the solar mixing angle, the measurement of the solar mixing angle. You can extrapolate here and imagine what it would be like if you were allowed to vary both at the same time. In both cases, we've assumed here the absence of NSI as the true hypothesis, but it's very clear that there would be a degradation in the precision. Even I haven't shown the plot of the sensitivity of JUNO within the absence of NSI, but I think it's quite clear from these plots what the difference would be. So let's move on to our combined analysis. So clearly the fact that NSI impacts solar neutrino experiments and reaction neutrino experiments in substantially different ways, this can be exploited to constrain these interactions. So in the absence of NSI, these measurements would be heavily dominated by JUNO. But as soon as NSI is included in the analysis, this picture greatly changes. And as we've shown, although the determination of the solar parameters is robust, it's still quite robust because matter effects and NSI effects would be subdominant, the precision of the measurement would be significantly degraded. Therefore, the precision goals of the experiment would not be reached. By contrast, solar experiments such as Hyper-K are incredibly sensitive to new physics which affects propagation of the neutrino, and as such, they provide very powerful tests for neutrino interactions during propagation. And this complementarity is what motivates a combination of both experiments as a way to constrain and to put bounds on non-standard interactions. So on the left here, I'm showing the sensitivity of oscillation parameters of a combined analysis of JUNO and Hyper-K. And what you can see is that these parameters can be measured as a sub% level. Now, again, I didn't show the plot of JUNO sensitivity in the absence of NSI. You'll have to take my word for it. But the combination of these two experiments in the presence of NSI means that you'd get a precision in the measurement of the solar mixing angle, which is very close to that which would be obtained by JUNO in the absence of NSI, so JUNO alone. What does this mean? It means that one of these parameters will be measured at this with this precision independently of the existence or not of NSI. Yes, the right-hand panel, I'm showing the sensitivity to NSI parameters after having marginalized over the oscillation parameters. And it should be noted here that the very large values of epsilon prime are excluded because we're talking about assuming an optimistic scenario where the mass ordering can be determined independently of NSI. When this constraint is relaxed, then you go into the LMA dark solution, which I'm not going to look at in detail here. Finally, I'm showing the remaining two-dimensional projections here, where you can see very clearly the inputs of each of the experiments, so Hyper-K in purple, JUNO in pink, and it can be clearly seen that, as we said, although the sensitivity of JUNO will not be greatly affected by the presence of NSI, low values of epsilons, which you can see on the x-axis, or I should have said on the y-axis, you have the solar oscillation parameters, on the x-axis you have the NSI parameters, and you can see that for low values of NSI parameters, this induces large shifts in the measurements of oscillation parameters by Hyper-K. So you can see where the two come together here. So in conclusion, I think I've convinced you that the complementarity between solar experiments and reactor experiments is a very powerful tool when it comes to constraining neutrino non-standard interactions. This combined analysis breaks the existing degeneracies. It would ensure robust determination of the oscillation parameters. We found that a combined analysis would allow a sub% measurement of the solar mixing angle at 90% confidence level and a 0.67% measurement of the mass splitting with the same confidence level. We also found that these results are completely independent of the experimental setup used by Hyper-Kamiokande. And we have also found improved bounds on NSI, which would be achieved by the combination, by a combined analysis of these two experiments. These improved bounds are shown here at 90% confidence limits, and these could be compared to either global fits and or to sensitivity studies that have been done for future experiments as well. And finally, again, although I didn't go into detail about it at all, we did look at the LMA dark solution and the possibility of constraining it using the difference in matter effects between Hyper-K and JUNO. What we found is that only a very small region of parameter space would be allowed at 1 sigma. However, this isn't enough to say that we could completely exclude this solution from the combination of these two experiments alone. And I'm completely out of time, so I apologize about that, but thank you so much for attending. I look forward to seeing you in the discussion section, and also stay tuned because the work that I shown here will appear very soon on arXiv. So thanks again.